Hi everyone. So in previous lecture we have discussed about this circuit and we have seen this circuit has the potential to mitigate the variation on VDD if you look at the I out current. Okay, and we also know that this I out current is basically K times the IDF current. And you also understood that for any current, any IDF current, let's say IDF is 10 microampere, K is 10, we get 100 micro of I out current. If you have IDF equals to 20, then you will get 200 micro of current. So for any current, this equation is satisfied. But what we want to uniquely define this current. Okay. So how we are doing? So first thing that we are doing, instead of K, what we are doing, we are assuming both the dimensions are same for M3 and M4, and it means these two currents are equal. The IDF is equals to I out, but we want a particular value of I out. Okay, so for that what we are doing, we are adding one resistor RS over here. So if you look at this circuit, if you look at this circuit, what we are doing first, the K is 1 here, so both the M3 and M4 dimensions are same. K is there, it will add another parameter, we'll see the equation. Okay, so along with that we are adding one resistor RS over here. Okay, so this is RS. So now as these two currents are same, or in general you can calculate this voltage from this side as well as from this side, both should be same. Okay, just a KVL. Okay, so we are doing that only. So basically what we are doing over here on this M1 side, this is the standard formula we know, and here we are ignoring actually the channel length modulation. So we have this VTH plus this factor. Similarly on this side, that is actually, so this whole quantity is actually your this gate voltage, let's say. Okay, and in this side what we have, this portion that is coming from M2, and the IR dot, that is I out times RS. Okay, so this current, and we assume that IDF equals to I out, so on both the side we have I out. Okay, now from this equation we can get finally this equation, and you can simplify it. Finally we'll have the expression for I out. Here you can see we have this factor K. Okay, so this factor coming to the picture, and also the RS. If you tune the RS, you will get a particular value of I out. Also you can play with K. Okay, all right. Now definitely we have ignored the channel length modulation over here, but as soon as in real case there will be some variation because of the VDD, but we can improve it. How we can improve it? We know if we have long channel devices, their channel length modulation is negligible, but the question is why? So we can understand it from equation itself, or we can let's first go through the equation. Simple equation that we all familiar with this equation, where this W by L is actually the effective length. Okay, so if you recall the structure of the MOSFET, okay, so you have channel length modulation. Okay, so in this region, what is effective L? Effective L is basically your this one. Okay, this one is the effective L effective. Now what is this? The total length L minus the delta L. So here we have the small delta L in this region. Okay, this is the delta L. So this L effective is basically N minus delta L. L is the total length. From there you can see, we can approximately, or we can write it as this is a derivation that you can see. Okay, but the main point what I am trying to convey is that if you look at this delta L by L, which is actually your lambda VDS, the channel length portion. Okay, channel length modulation portion is coming from this part. Okay, so this reduces if you increase the L. Okay, so higher the length, your channel length modulation effect is reduces, and we can approximately say ki this is the expression of our I out, and there is very less dependency of VDD variation on this expression. So we have supply independent current. We have something called supply independent current. Okay, that is what we're actually started with. Now another point. So instead of using the resistor over here, what we can do, we can use the same resistor RS over here. Okay. One point you should note: this is the current source and this is the diode. Similarly here, this is the diode, this is current source, M4 is current source. So we are adding this resistor RS on the current source. Okay, this is a dependent current source. So here also the same thing that you need to do. We just need to flip this two transistor over here. So now this is your current source, this is the diode. Okay, you can see, and here this is the diode, this is your current source. So I am adding this RS resistor over here on the current source. Okay, so now here also what you can see, what is the problem with this? The problem is that we know all that this transistor having this body terminal, right? This body terminal, let's say this one, the body terminal. Okay, now for NMOS, we all know from the layout point of view, this all body terminals are connected together. Okay, all body terminals are connected together, and they are connected to ground, common ground. Okay, now definitely if you look at this portion, there is some body to source voltage, whereas here body to source voltage is 0. Okay, because of that you have something called the body effect. Okay, but in case of PMOS, for each individual PMOS, you can get that body terminal, and you can manually connect this body terminal with the source terminal. Okay, so that way you can avoid the body effect. Okay, so in other words, we can say in this particular expression, the VTH1 and VTH2 are the same, we can say, and we can directly cancel this 2. Okay, so that is what we assumed, and we cancel this 2 and we got this equation actually. Okay, so that is valid only when or if you use this RS over here instead of using it here. Okay, rest of the things are similar, and yeah, I hope you understood.